Thank you all very much, and good afternoon, everybody. My name is Travis Carrigan. I'm a Senior System Sales Manager for Cadence Design Systems. I'm joined by my colleague, Erick Gantt, Senior Principal Application Engineer. And today we're going to be talking to you about accelerating your CFD meshing process using Fidelity Pointwise. All right, so you've all seen me present this quote probably a half dozen times at this point, including last year, and there's good reason. You know, this quote comes from the CFD Vision 2030 study, and I think it really sums up, you know, the vision for, you know, how we develop computational software, but also, you know, for the industry as a whole, and that is that a single engineer should be able to conceive, create, analyze, and interpret a whole bunch of related simulations in a time-critical period without having to manually manage all of those simulations and then do that to a pre-specified level of accuracy. And one of the ways that we're addressing this at Cadence is through our Fidelity platform, kind of an end-to-end solution framework for, you know, geometry pre-processing, meshing, running calculations, you know, optimization, post-processing. And the technology portfolio is pretty vast, including things for design and geometry and mesh generation and different solvers and optimizers. But today, as the title suggests, we're going to focus on Fidelity Pointwise, which is our independent CFD pre-processing tool that really represents, you know, 40 years of mesh generation research and development, and has one of the most comprehensive suites of meshing features out there, from geometry import, bringing in geometries from a variety of sources, exporting to pretty much every CFD solver, including SU2, the ability to generate all different kinds of meshes, you know, multi-block structured, hybrid, overset, curved high order meshes, perform grid adaptation, and even automate the entire meshing process using our glyph scripting language. And if you talk to some of our clients, and some of you in the room there are using our software as well, the three things we hear most frequently are, you know, we're using it for its flexibility, being able to work with a variety of different tools, you know, a lot of I/O flexibility, the ability to integrate with a process. So you've already identified and started to piece together a CFD process, and you want, you know, Pointwise to integrate very seamlessly with that. And then the control it gives you over the meshing process, right? If we look at Pointwise specifically and kind of the vision for that product, it really stands upon three pillars. The first being automation. You know, we're working very hard to reduce the amount of manual intervention for mesh generation. Acceleration, you know, improving your meshing turnaround time, and then innovation, developing novel solutions to improve your simulation's outcome. And this, again, really builds to the vision of user independent and suitable for purpose meshing, meaning it doesn't matter who sits down in front of the tool. At the end of the day, everybody would be able to generate a mesh that is suitable for its intended purpose, right? And so that really speaks to Flashpoint. And I introduced this last year in the surface meshing component, but Flashpoint is our suite of goal-oriented meshing tools built in Pointwise. Again, we started with surface meshing. You bring in a geometry, you prepare that geometry, you set up some meshing goals, and you can automatically generate a watertight and high-quality surface mesh that adheres to those goals. And it really gives you the ability to build recipes and encapsulate best practices to work on parametric designs, configurations, do grid refinement studies like this. And at the end of the day, it really accelerates the meshing process. So something like this drone, where it may have taken hours or days or weeks before to generate a mesh like this, now in a push of a button, we can generate a surface mesh automatically with anisotropy, and 120 million cell volume mesh in 30 minutes on a laptop using our T-Rex algorithm for the viscous region, and then the voxel technique kind of for the off-body region. So that kind of serves as a recap and an intro into Flashpoint. I'm going to turn things over to Erick, and he's going to talk about some of the enhancements that we've made since we spoke to you all last year to automatic surface mesh, but also some new capabilities in Flashpoint. So Erick?
All right, thank you, Travis. Let's go ahead and jump right on into our next slide here. So as Travis mentioned, this is our goal-oriented meshing tool, automatic surface mesh. We've made some recent changes, and this slide kind of overviews those changes. Essentially, some organizational work that we've done, some renaming of tabs, as you can see at the top right of the image on this slide. But the main tools the powerful tools that we've added recently are a mapping filter and a stretching filter, and that's kind of what I want to focus on here for this part of our talk. This next slide gives a breakout of the Surfaces tab of Automatic Surface Mesh, and specifically a new mapping filter tool, which gives the user now the ability to have influence over a process in Automatic Surface Mesh previously that was all automatic. And so now you can specify which long, thin, narrow types of surfaces that you prefer to have a special treatment that we call mapping. And in particular, in the middle of this table, you'll see there's a column labeled pattern, which gives you the ability to specify a string in there that's matched against the naming of the surfaces in your geometry, and gives you an automated control, especially with our glyph scripting language. So jumping on to the next piece that we've added for Automatic Surface Mesh is the stretching capability. This is the third tab of ASM, the Boundaries tab. In the previous release of Automatic Surface Mesh, you really only had 3 classifications: curvature, convex, and concave, for the boundaries of your surfaces. That was set up for you automatically, and they were either on or off. It was an all or nothing setup. And we realized pretty quickly users needed to be able to control that a little bit more and have some customization. So in the latest release, we've added the ability to add custom stretching filters. And again, here for this feature at the bottom of this image, this table at the bottom allows you to, again, enter patterns to match the naming of your surfaces in your geometry and give you a more automated control. And again, with our glyph scripting language, you can automate this process very nicely. And so moving on, I have just a couple of examples here of some of the things that we ran into in our previous release of Automatic Surface Mesh. This geometry that you see here, there's an image of full geometry at the top right. It's kind of a drone concept vehicle that we've used for a recent training class that we have. The leading edge and the trailing edges of this particular geometry have long, narrow surfaces, which we often see, but in this particular case, the boundaries of those surfaces are rounded. They're not truly convex with sharp edges. And so what happened in our original release of Automatic Surface Mesh is in the bottom right image, you can see it would apply stretching on the trailing edge at the top and the bottom. And as those T-Rex anisotropic layers came together, it was trying to fill in with triangles, and you could get some skewing or large angles in those cells. And the table at the top left does indicate that for max angle over 150 degrees, we've got almost 350 cells. And so this was the sort of thing that we wanted to address with our newer capabilities in Automatic Surface Mesh. This next slide actually shows another area. This goes to the stretching filter that I mentioned on the third tab of Automatic Surface Mesh, where convex, concave, and curvature edges are classified automatically, and it would apply stretching to those boundaries with our T-Rex anisotropic meshing. And it was either an all or nothing setup. You could either have all of those boundaries treated that way, or you had to turn them all off. And we quickly realized you need to be able to customize that. And this was just an example of an area of this geometry where you may not want that stretching applied. And so this slide goes back to that trailing edge of the geometry. On the left, we see the original situation where we did not have the mapping applied. On the right, we've told it specifically we want mapping on the trailing edge. And even better, we told it how many points we want to apply there. And so we get a much better quality surface grid on that trailing edge. And if you look at the tables at the top, we went from almost 350 max angle cells in this geometry down to none for the new capability that we have, which is really nice. And so just kind of to wrap up Automatic Surface Mesh discussion here, this is all the surface grids for this particular geometry. We get a really nice matching and blending across the surface grids at their junctions, a nice clustering where we need it. Setup for this was just a minute or two. It took about a minute on my laptop to generate the surface grids. and we're off and running and ready to create a volume grid for this case. So speaking of which, let's jump right on into automatic volume mesh. This is a brand new capability for our Flashpoint set of tools that allows you to take your surface grids and very quickly set up a volume grid, or what we call in Pointwise a block. On the left-hand image, when you come into this command, it lets you choose whether you're doing an external flow or an internal flow. In other words, do you need it to create new FAR boundaries, or are the surface grids your FAR boundaries? In our example that you see at the right for this drone concept, we have an external boundary that we're creating, and so we choose the first option. And in the middle of this slide, you can see just an example image of the panel. We'll talk about it a little bit more. I think the most powerful capability for automatic volume mesh is this ability to have more control over boundary conditions to set up your volume grid for the 3D version of T-Rex anisotropic meshing. And even though this table, for those of you that may have used this tool, even though this table at the top looks pretty much like the one in our solve command where you set up T-Rex outside of AVM or automatic volume mesh, it has a special additional capability in that for the selected new boundary condition, you get a new table at the bottom of this panel that again lets you do pattern matching. And so if you've used automatic surface mesh to create your surface grids or your domains in Pointwise, the naming of your quilts is applied to those domains or surface grids, and that follows through into automatic volume mesh. And again, you can use pattern matching to select those surface grids and set up your boundary conditions in a very automated fashion, which I think makes this tool very powerful for automating your meshing. So kind of a overview here is the main panel on the left-hand side, just showing you some of the tools for automatic volume mesh. At the top, you can choose whether you're going to use a Delaunay-based tetrahedral field grid or our voxel method for the field. Just below that, you can choose the shape of your FAR boundary. I've chosen rectangular, as you can see in the image. However, on the far right, there's example images of the panel and what it looks like if you choose either cylindrical or spherical as well. And in the middle of the panel, denoted with the little arrow, is a selection there where you're actually telling it that you want to use the T-Rex method for your boundary layer or near wall meshing to get a nice viscous cluster. All right, so for our drone case, setup of this takes, again, just a few minutes. Saving that particular block topology and then initializing it takes an additional about 14 minutes to get almost about 30 million cells for this example. We can see the voxel mesh imprinted on the boundaries in the left image of the slide, and on the right, a slice through the interior. And you know, I think the key factor here is just how quickly you can set up these processes with ASM and AVM, and probably in about 16 minutes or so total, you've got a really nice volume grid to work with and send into your solver. A couple of cuts, additional cuts through the interior of the voxel topology. Here I'm just showing cells by color. The blue is your hexes, the red are tetrahedra, the yellow are your pyramids, and then green, you see some green near the body, those are prism cells. And so let's go ahead and move on to really one of our newest features that came out with 18.6 of Fidelity Pointwise, and that's accelerating the anisotropic meshing. And in terms of the GUI changes, it's a pretty simple change. This slide shows you an example image of our solve command for unstructured blocks, and specifically the T-Rex tab where you set up all the parameters for anisotropic meshing. And at the bottom of the right image, you can see the acceleration frame. It has a setting on the left, which is the default. We call it quality. All the way to the right, we call it performance. So on the left, the default is layer subdivisions of 1. That basically means the anisotropic meshing is advancing 1 layer at a time performing all of its quality checking and smoothing with each layer. As you move that slider across to the right, it's going to jump over multiple layers or advance multiple layers at once. And so it cuts out some of that checking, some of that smoothing, some of the smoothing that's going on. And in that way, it accelerates the process. But as the slider labels indicate, you may lose a little bit of quality as you accelerate it. But we have seen for a number of cases in our testing up to 3 times performance speed up. So my last slides here are going to talk about unstructured block smoothing. And here we have a new command in the solve panel called smooth. Allows you to go in and take advantage of our WCN algorithm that was put into Pointwise specifically for our high order export. And what I want to do is just go ahead and jump over and talk about the primary tool or control for this, and that's the cost angle threshold. This actually goes in and looks at all the cells in the unstructured volume and classifies them and chooses the ones that exceed that measure, and those are the only ones that actually get smoothed, and it makes the algorithm much more efficient. And so my last slide here is just showing for our drone example, on the left-hand side, for that particular volume that we looked at just a few slides ago, the max included angle was about 177 degrees. And after 2 runs or 2 passes of the smoothing, we've gotten it down to about 175.5 degrees, which, as many of us know, for a flow solver, or even a single degree can make a huge difference in getting a solution. All right, so that's it. I think I might have run a little long. If we have any questions, I think we can take those now. Travis and I can help you with any questions you may have.
Thank you very much, Travis and Eric. Let's see if there is any question from the audience. No question, no break. No, you have a question? Yeah, there is Tom.
Yeah, Eric, can you go back to the I forget what you call it, the cost angle something, the metric that you guys used to do that last optimization for the unstructured blocks? What was the angle that you're using?
So I was trying to go back here to the slide, but it looks like I'm not able to. But for this particular example, I actually set it down to 173. I found that because it's evaluating the cells and determining which ones are going to be smoothed, you want to keep the number, the threshold fairly close to your existing values so that you're not overshooting and adding, a large number of cells into the smoothing algorithm. I believe this is the default, the 175, but I think for my example case, I actually had it set to 173.
Yeah, just to clarify, so is that just maximum included angle? I see that on the next slide. Is that the definition of that?
So it's not exactly the same as the calculation that we have in the examine command for max included angle in the examine command, but it is very close. And we're actually looking at adding a new diagnostic in our examine tool that is exactly the same as this cost angle threshold so that users can get a one-to-one comparison.
Got it. Great.
Thank you, Tom. I also, is there a question? No. Yeah. We have a question.
Just a quick question. Is there Python-based scripting support for mesh generation?
So Travis, Eric, the question is that, is there a Python script-based system for supporting mesh generation?
I'm sorry, I didn't catch the first part of that. Is there a way?
Python, I heard it was, the question was, is there a Python scripting support? And out of the box, the glyph scripting language is TCL based, but if you go to our GitHub page, we do have an open Python API that you can leverage if you prefer kind of that implementation.
Okay, thank you. I've also, there is another question.
The question So is it possible to use boundary point machine to mesh and especially instead of having it generate?
So the questions are actually also in the chat. You should be able to read. The first question is about the usage of AVM capability. 2.
So to use boundary point machine to customize profile. Pointwise that.
So if it's possible to use the AVM capability with a customized far field, this is the question.
Currently, it is not set up to have a customized far field. We only have those 3 specific far fields that you can choose: the rectangular, cylindrical, and spherical. You can adjust the values and specifically set those 3 up as you need to. But if it was a custom shape, that would not be possible. Now you can come into that command with surface grids that you want to use for an interior flow. And so in that way, you've obviously controlled the far field boundary. But for an external flow, you would have to use the settings and tools that we have currently. I hope that answers.
Yeah. There is also another question. The audience started becoming active.
Yes, so they would like to ask if there is a possibility of changing the doing this.
So the question is about possibility of changing the growth rate of the boundary layer during the extrusion process.
So we do have a customizable glyph implementation for controlling the growth rate for that extrusion process to develop those layers near the body. That is something that currently can only be done through the scripting capability glyph and is not set up in the GUI right now, although we're looking at possibility of adding that to the interface. We call that growth profiles, the setup that we already have for scripting. It's called growth profiles.
Thank you.
Sure.
Last question? Not? Maybe we can make a further applause.
I just have one comment for you guys, Travis, Eric. Thank you for coming on and speaking. Thank you for supporting the community, the SU2 community, and in particular being a foundation sponsor. So we really feel your support, appreciate it. Hope we keep this relationship for a long time to come. So thanks again.
Absolutely. Thank you.
Yeah, thank you.